I believe we got through problem number 42, yes?
No, we didn't do the problem.
Uh-huh.
Wait, are we testing tomorrow?
Part 1 is tomorrow.
Yeah, well, big part of it.
Okay. We'll start off with problem number 44. 6e to the 2x plus 1 plus 9 equals 15. And with these here, we want one term on either side. So we're going to need to move everything away from e before we can do anything else. Now, we're not so much concerned about the 2x plus 1 because it's in the exponent. So the first thing we're going to want to move is the plus 9. And to do that, we're going to subtract 9 from both sides, leaving us with 6e to the 2x plus 1 is equal to 6. Now we still have that multiplication of 6, so to simplify it, we're going to divide both sides by 6, leaving us with e to the 2x plus 1 is equal to 1. We want to get that e by itself first. Now we're not so much concerned with the exponent because we're going to use logarithms to get the variable out of the exponent. Questions on how we got to this point so far? At this point here, we're going to apply a logarithm to both sides. And since the base is e, we're going to use the natural log. We're applying natural log to both sides. And according to our power properties of logarithms, we can move the exponent to the front, telling us that we have 2x plus 1 times the natural log of e is equal to the natural log of 1. Questions on this so far? Now, part of the reason we applied the natural log of e to, or natural log to both sides, is because of the natural log of e. So we can grab a calculator, say the natural log of e to the first, or just e, is 1. So this is going to simplify to 1, giving us 2x plus 1 times 1, which is just 2x plus 1. And pretty much for every single problem, we leave the natural log of whatever the number is by itself, because if I take the natural log of 1, we're going to get an irrational number, yes? And what is the natural log of 1? 0. So one of the nice natural logs that's not taking the natural log of e is 1. Really, log of 1, no matter what the base is going to be 0. So this is one of the few cases where we can actually simplify natural log of 1 as 0 and solve. So we subtract 1 from both sides, telling us 2x is equal to -1. Divide both sides by 2, telling us x is -1/2. Even if we had left it as the natural log of 1, we'd have got x is equal to the natural log of 1 minus 1 all over 2. 1. Natural log of 1 minus 1 all over 2 is still -1/2. We get the same value. Questions on this one here? All right. Let's go on and look at 45. 7 to the x is equal to 3. Now, because this one here does have one base on either side, we don't have to do anything to get those bases by themselves. And because the base is not e, we can apply a log to both sides. And specifically, the log that we want to apply to both sides is going to be log base what? 7. log base 7. And the reason we're applying a log in doing this is to get this variable out of the exponent. The power property of logarithms says we can move the exponent to the front, telling us that log base 7 of 7 to the x is the same as x times log base 7 of 7. And well, log base 7 of 7 is 1. It simplifies to 1 times x, or just x, telling me that x is equal to log base 7, not 3, 7 of 3. X is by itself, so we are done there. Now, if we wanted to, we can approximate. We can grab the graphing calculator, say math, log base 7 of 3 is 0.5645 or 0.565. And those are our answer choices. Those are our two answers. Questions on these here? Be ready for the next one. Why not? Let's look at 46. (11 to the 6x plus 2 is equal to 38. Now we do indeed have one base on either side, so we don't have to move anything. We don't have to add, subtract, multiply, divide. We can go on and apply a logarithm to both sides. Specifically, log base what? 11. And for the left-hand side, we're going to take that exponent and move it to the front. So we're going to apply log base 11 to both sides, use our power property on the left-hand side. To rewrite it so that we have 6x plus 2 times log base 11 of 11 is equal to log base 11 of 38. Again, log base 11 of 11 is 1. And that's nice because it tells us that the left-hand side is just going to be 6x plus 2. The right-hand side, log base 11 of 38, we're going to keep it as log base 11 of 38 because, unfortunately, if we check log base 11 of, it's not a nice number. It's irrational. So we'll leave it as this here. Now we need to get x by itself. Because we don't have an x squared term, we're not going to get it equal to 0. We're just going to move everything over to the other side. So the first thing we'll need to do is subtract 2, telling us that 6x is equal to log base 11 of 38 minus 2. We're not going to subtract the 38 by the 2 because the 38 is inside the log and the 2 is outside. And then lastly, we're going to divide both sides by 6, telling us x is equal to log base 11 of 38 minus 2, all divided by 6. And that's our final answer. If we want to get the decimal approximation, we can just grab the calculator, alpha y equals enter. We'd have log base 38 minus 2 all over 6, which is equal to negative 0.08505 or negative 0.081. Questions on this here? Questions on any of this so far? Why not, while we're here, we'll go on and look at 47 also. Natural log of 3x plus 2 is equal to the natural log of 4x minus 5. Since we have one log on either side, they are the same log. Well, the only way these two can be equal is if what's inside is equal as well. So really all this is saying that 3x plus 2 is equal to 4x minus 5. Again, we don't have quadratic terms. We don't have x squared, x cubed. We can get x's on one side, constant terms on the other. Doesn't matter what we do first. We can add 5 to both sides. We could subtract 2. We could subtract 4x from both sides, or I'm going to subtract 3x from both sides. 3x minus 3x is 0, telling us 2 is equal to. 4x minus 3x is going to be x minus 5. Then we would add 5 to both sides. Those would simplify, telling us x is equal to 7. That's it. There is no approximating. There's nothing we have to do with it. That's our final answer. If we wanted to, we could have checked this here. I'd grab the calculator and just plug it back in. So the left side would be log of 3 times 7 plus 2. So when we plug 7 into the left-hand side, we get this number here. We can do the exact same thing to the right-hand side. Log of 4, but instead of having x, we're going to replace it with 7. Minus 5 is this here. They are the exact same value, so the left and right side have the same value, which means 7 is the solution. Questions on 47? We feel comfortable with 47. Questions on 48 or 49? If you have time, go on and work those, because these are exactly the same thing we did with 47. You'll get a little more practice with those. However, I do want to look at 50. Log base 2 of x squared minus x minus 6 is equal to log base 2 of negative x. Because the logs, we have one log on either side, and they are the exact same logarithm, the only way they can be equal is if what's inside them is equal as well. Now this is a little bit different because we do have an x squared term, and because we have an x squared term, we need to get this equation equal to 0. So I need to move this negative x to the other side, and to do it, I'm going to add x to both sides, because our negative x plus x is indeed 0. Interestingly enough, on the left-hand side, our negative x plus x is also 0. Really telling me that my equation is x squared minus 6 is equal to 0. Now at this point here, we could try to factor it. It does not factor. Do I have a middle term anymore? No, we don't have an x term, which means I can use the square root method. We can get that x squared term by itself and then square root both sides. So I'm going to add 6 to both sides, telling me that x squared is equal to 6. Square root both sides. Square root of x squared is x. Cannot take the square root of 6, but because we took the square root of both sides, we do have to add the plus or minus. Now realistically, the plus or minus is telling me that I actually have two answers. Really, we're saying that x is equal to the square root of 6 and x is equal to the negative square root of 6. We started off with logarithms. We cannot have a negative inside the log. So if we look at both of these answer choices, well, we're definitely going to need to check it, and most likely, which one's not going to work? The negative. So let's start with it. Because if we plug it back in, we would get log base 2 of negative square root of 6 squared minus negative square root of 6 minus 6 is equal to log base 2 of negative square root of 6. We replace every x with negative square root of 6. Now let's go piece by piece through it. Negative square root of 6 squared is going to be 6. If you're not sure, we can plug it in. Our middle term, negative square root of 6 is going to become positive square root of 6 minus 6. Now inside the parentheses here, our 6 and negative 6 are like terms, and they will become 0, leaving us with log base 2 of square root of 6. On the right-hand side, negative square root of 6 would be positive square root of 6. And yes, log base 2 of the square root of 6 is indeed equal to log base 2 of the square root of 6. Interestingly enough, x equals negative square root of 6 does work. We're not taking the logarithm of a negative number, so we are good. While we're at it, might as well check the other case. Log base 2 of the square root of 6 squared minus the square root of 6 minus 6 is equal to log base 2 of negative square root of 6. On the left-hand side, our square root of 6 squared would be 6. This would become minus the square root of 6 minus 6. And the right-hand side is just going to become square root, or log base 2 of negative square root of 6. Again, 6 and negative 6 would cancel, telling me that the left-hand side is going to be log base 2 of negative square root of 6 is equal to log base 2 of negative square root of 6. Is this a true statement? No. And it's not so much that both sides are equal. I cannot take a log of a negative number. So it doesn't matter that the fact that both sides have the same statement. It doesn't matter, because log of base 2 of negative square root of 6 does not exist. Neither side exists, so it can't be a true statement. So incidentally enough, the positive case does not work this time, but the negative case does. So the only solution for this is negative square root of 6. I put this in here to show that, yes, the negative case could be the one that works. We do need to check both to make sure. Any other questions on 50? Let's look at 51 through 56. So if we look at 51, we need to get the logarithm by itself. Everything else on the other side. Well, it is. And once we get to this point, we want to put both sides to the base, or put both sides to the base of the logarithm. And since the base of the logarithm is 7, we're going to put both sides to the base of 7. So 7 to the log base 7 of 4x plus 9. 7 and log base 7 would cancel, telling us that 4x plus 9 is equal to 7 squared. Now, luckily for us, 7 squared is a nice number. It is 49. Don't have an x squared term, so we don't need to get this equation equal to 0. We just need to solve for the value of x. And the first thing I would do is subtract 9 from both sides, telling us that 4x is equal to 40. Then we would do what? Divide both sides by 4, telling us x is equal to 10. Questions on this here? Say we weren't sure, we could always go back and check. Math. Log base 7 of 4 times 10 plus 9 is indeed 2. That's what the equation told us it needed to equal, so we're good there. Any other questions on 51? Why not? Let's look at 54. Natural log of 6x minus 4 equals 15. Since we do have two terms on the left-hand side, we have that natural log of 6x. That minus 4, we need to move it to the other side. So we're going to add 4 to both sides, telling us that the natural log of 6x is equal to 19. At this point here, we need to put both sides to the base of the logarithm. And since we're talking about a natural log, its base is understood to be e. Because e to the ln of 6x, e and ln will simplify out, telling us that 6x is equal to e to the 19th power. Well, e is an irrational number, so multiplying it by itself 19 times is not going to make it any more, or not going to not make it irrational. It's still going to be an irrational number. So we'll leave it. Solve for x. Last thing we got to do is divide both sides by 6,
You're checking out.
telling us that x is equal to e to the 19th divided by 6. If we wanted to see the decimal approximation, we would get this massive number here. 29,747,050.16, and it's going to keep going on. We don't get more than 2 decimal places here because, well, it kind of ran out of room. Any other questions on 50 through 54? All right. We're going to look at 56. Now, 56, the big thing with it is we have 2 logarithms that are being added together. For us to be able to solve, I need this as a single log. And whenever we have 2 of the same log being added together, we can rewrite it as a single log with what's inside being multiplied together. So log base 2 of x plus log base 2 of x minus 2 can be rewritten as log base 2 of x times x minus 2. Now we can do the same steps we were doing, and that we're going to put both sides to the base of the logarithm. Since the logarithm's base is 2, we're putting both sides to the base of 2, because our 2 to the log base 2 will simplify, leaving us with x times x minus 2. And that's going to equal 2 to the 3rd power. Questions on this here? Now we need to multiply. On the left-hand side, we're going to distribute x times x is x squared. X times negative 2 is negative 2x. And 2 to the 3rd is 8. Now, because we do have an x squared term, and specifically we do have a middle term, unlike the last time, we will need to get this equation equal to 0. Telling me that x squared minus 2x minus 8 is 0. Now we need to factor and solve. All the ones on the test will be factorable, graphable, if we do have a quadratic, or completing the square. Not completing the square root method. You won't have to use quadratic formula or completing the square for any of them. You can, don't have to. If we factor this here, there is no greatest common factor amongst these 3 terms. So we can go to our 2 sets of parentheses with 3 spaces. Since the 3rd term is negative, our signs are opposite. Factors of x squared are x and x. Factors of 8 are 1 and 8, or 2 and 4. Yes, we would want 2 and 4. We would want the 2 positive and the 4 negative. If I checked it to make sure it matched up to the middle term, x times negative 4 would be negative 4x. 2 times x would be plus 2x. And positive 4x, or negative 4x plus 2x, negative 4 plus 2, would be the negative 2x that we wanted. Now, because we do have two things multiplied together to equal 0, one of these two is going to have to be 0. Subtract 2 from both sides, telling us x is equal to negative 2. For x minus 4, we would add 4, telling us our two solutions are negative 2 or 4. Now, especially since we use the product rule and we do have positive negative cases, it's going to be helpful to check these. So our original statement, log base 2 of x. So log base 2 of negative 2 plus log base 2 of negative 2 minus 2 is supposed to equal 3. Really, at this point, we could have already said it didn't work. Log base 2 of negative 2. There's nothing I can do with it, nothing I can simplify it any further. I'm taking logs of negatives, so we can throw it out. I cannot take the logarithm of a negative number. And we can check the other side. Log base 2 of 4 plus log base 2 of 4 minus 2 equals 3. And if we simplify down what's inside each of these parentheses, we get log base 2 of 4 still, plus log base 2 of 2. What's inside both of those logarithms is positive and not 0, so this works. Incidentally, log base 2 of 4 is 2, and log base 2 of 2 is 1. 2 plus 1 is indeed 3. So this one does work. So our only solution for this here is x is equal to 4. Questions on this here? We ready for the last piece of solving? Inequalities. Now, inequalities aren't any different than what we've been doing. The only main thing we have to pay attention to is if the variable starts inside of a logarithm, because if it starts inside a logarithm, what's inside the log, in this case x minus 1, those values of x has to be greater than 0. X minus 1 cannot be 0 or negative. Any value of x that makes that expression be 0 or negative has to be removed. So here we would add 1 to both sides, saying x has to be greater than 1. Now the question is, why do we even need this when we didn't do it for equations? Well, equations told me it's either this value, one value, or this other value. So we had 1, 2, we had a handful of solutions, and we can plug them in and check them individually. An inequality is a set. We have a whole group. As long as they're greater than this number, less than this number, all values work. We are not able to check all of those values. We're not able to plug them, realistically plug them all in. So on those where we have so many solutions, we need to figure out which ones don't work so we don't have to check all of them. We're just saying if it's smaller than or less than or equal to 1, we got to remove them. We have to throw them out. Now that that's taken care of, we can go on and solve. We have one term on either side. We do have a logarithm that we need to get the variable out of. So we're going to put both sides to the base of that logarithm. Since the base of the natural log is e, we put both sides to the base of e. And our e and natural log simplify out, telling me that x minus 1 is greater than or equal to e to the 9th. Luckily for us, x is not being squared, so we just need to get x by itself. And to do that, we will add 1 to both sides, telling me that x is greater than or equal to e to the ninth plus 1. Now the question is, do the restrictions come back into play? Is 1, because 1 wouldn't work, the question is 1 greater than or equal to e to the ninth plus 1? I have a feeling no, because unless e to the ninth was negative 1, there's no way I can add 1 to it and get this to be true. The other way we can check is just plugging it in. E to the ninth plus 1 is over 8,000, so it is not bigger, or it is not smaller than 1. 1 is not bigger than it. So since the restricted values do not come into play, or not part of our solution, we don't have to add that statement in. And the only solution for this is that x is greater than or equal to e to the ninth plus 1. Questions on this here? While we're at it, we can go on and look at 58. Restrictions. What's inside the logarithm? X plus 2 has to be greater than 0. Or realistically, we're saying that x has to be greater than negative 2. That's fine. Now to solve it, we're going to put both sides to the base of 7. 7 to the log base 7 simplifies out, telling me that x plus 2 is less than 7 to the 4th. Is 7 to the 4th power a nice number? Well, if we're not sure, we can plug in the calculator, and it is 2,401. That's a nice number. Solve for x. Telling us x is less than 2,399. Questions on this here? As we did start with the log, we do have restrictions, so let's check them. So what's the value of x we cannot have? Negative 2. Is negative 2 less than 2,399? Yes. Which means we do have to throw that restriction statement on it. It doesn't matter what we checked. As long as we checked a value that is a part of the restriction, that would make that x is greater than negative 2 false. We have to remove them. Yep. Questions on 57 or 58? How do we feel about our logarithmic inequalities? We feel good with 59 and 60? Either one of these that we want to see? 59. 6 times natural log of x plus 7 is less than 60. Again. Restrictions. X has to be greater than 0, because the only statement or only equation we had inside the logarithm was x. We're not going to worry about the power property moving it back up. This is what they gave us. This is the starting problem. If it had started out as the natural log of x to the 6, we would treat it differently, because that's the original starting problem. This is our original starting problem. But I would want to get x, this natural log, by itself first. Always start off with addition, subtraction. So the first thing I would do is subtract 7 from both sides. Then we would do what? Divide both sides by 6. Telling us that the natural log of x is less than 53/6. I can tell you this, 53 will not divide by 6 nicely. Because for it to divide nicely, evenly, 6 needs to be a factor of 56. Our factor properties of 6, that number has to be divisible by both 2 and 3. 53 is not divisible by 2. So it's not going to be divisible by 6. Or if I wanted to, yeah, we're better off just leaving it. Now to get x out of the logarithm, we need to put both sides to the base of e, telling me x is less than e to the 53/6. Questions on this here? Now we do need to check our restrictions. Let's see, is 0 less than e to the 53/6? Well, we know e is a positive number, so this is definitely true. So we have to say that 0 is less than x is less than e to the 53/6. Any questions on these here? Let's go good with this. We're ready to move on to the last ones. Let's look at 62. Now the nice part about 62 is that the variable starts in an exponent, not inside a logarithm. And the reason I say that's nice is because we can put whatever number we want into an exponent. There are no restrictions on those. So I don't even have to look at restrictions. I can go on and make sure and get both sides to have one term. We're already there. So now we can apply a log to both sides. Specifically, log base what? 3. And the reason we do that is so that we can get the variable out of the exponent. Because I can move that 4x minus 5 to the front, telling me that I have 4x minus 5 times log base 3 of 3 is greater than log base 3 of 108. Did I really need to write log base 3 of 3 in the second step? Not so much, because what is log base 3 of 3? 1. Really telling me that 4x minus 5 is greater than log base 3 of 108. Likely for us, we don't have an x squared term, any higher degree polynomial expressions, so we just need to get x by itself. We can do that by adding 5 to both sides, telling us that 4x is greater than log base 3 of 108 plus 5. And lastly, we would divide both sides by 4, telling us x is greater than log base 3 of 108 plus 5 all over 4. And that's it. Now, for the most part, we'll leave it as this here. Now, I could come over to the graphing calculator, math, log base 3 of 108 plus 5 all over 4, and I get this here. Luckily enough for us, because we are saying greater than, if we're going to 3 decimal places, that's even better, because 2.315, the 4th decimal place is a 4. So if we were going by pure rounding rules, less than 5, so we round down. However, because it is an inequality and we're saying that this number has to be bigger than it, from the little bit of research, or kind of what I've been looking into, it said it wanted us to round to 3 places. I go to the 3rd place. Since we're talking about greater than, we round down. I don't even look at the 4th. The 4th could have been a 5, and I'd still round down, because we're saying that the values of this here have to be bigger than this amount. So if we'd have rounded, because it's round up and down, it gets a little tricky in how we do it because of inequalities and how inequalities work. So in my opinion, we're better off not even rounding, just leave it as that, because yes, x is bigger than that. We don't have to worry about rounding up or down based off of it being greater than, less than, so on and so forth. Does that make sense? Questions on this here? And really that's it. The rest of them are the exact same as this here. It's just using natural logs instead of logs. Nothing else really changes. I do have the full review video up already.